Yeah.
can get a video and everything. There we go.
Okay. So let's start then. So it's a pleasure to have Zack Sylvan from Columbia University. He's going to tell us about homological mirror symmetry near SYZ singularities. So Zack, please.
All right, thank you. Thank you for the invitation. I'm glad to finally be able to give this talk. So yeah, I'm going to talk about particular local singularities near which these appear in the Gross-Seibert program, and near which we're now able to understand homological mirror symmetry. So this local model is given by the spaces product of some x's is 1 plus sum of some y's. Oops. So these x's live in Cm plus 1, and the y's live in C star to the n. And kind of the tools from the Gross-Seibert program produce these local models and tell us that we should expect xmn and xnm to be mirror. So we want these to be mirror, but not just kind of abstractly. We want them to be mirror in a way compatible with family Floer theory, which really means gluing SYZ fibrations. What this would let us do is, if we have some kind of more complicated Calabi-Yau, we find this kind of toric degeneration, we cook up these local pieces, we have hopefully a recipe for gluing them back together that is not part of this problem, that is part of the reconstruction problem in mirror symmetry. But once we have a recipe for how to glue this together, we can ask whether kind of Floer theory reproduces that recipe, and if it does, then we can get homological mirror symmetry in a tautological way, and that's kind of the goal of family Floer theory. So concretely, what we need is a closed torus-like Lagrangian brane for each point in the mirror. Okay, so well, why don't we start with a couple examples of what sort of structures we're expecting. Oh, that's an issue. Let's try it that way. Okay, so the simplest case is x0n. So x0n, we still have an x, it's x0, is 1 plus y1 plus yn. And this thing is just C star to the n with coordinates yi, or yj, sorry. Right? Kind of this hypersurface is cut out by an equation for x0, so it drops out. We similarly have xn0, which, well, we know C star to the n is self-mirror, so we should expect xn0 to also be a copy of C star to the n. So let's see that. x0 times up through xn should be equal to 1, and now there aren't any y's. And so this thing is indeed a copy of C star to the n. This time kind of with coordinates x1 through x, I guess xn in this case. So we can, again, solve this equation for x0, and we get coordinates on this mirror xn0. All right, simple enough. Let's do x11. So x11 is given by x0, x1 is 1 plus y. So that's the same thing as, x0, x1 is not equal to 1, since y is something in C star. So this is C squared minus a conic. And this is well known to be self-mirror. Okay. I'm going to do one more example before talking about the general situation, and that's x12. So x12 is, well, x0, x1 equals 1 plus y1 plus y2. And it's not so easy to see what's going on here, but one thing we can notice is that there are two C star cubed charts. They're given by x0 is not 0, and by x1 is not 0. This is ridiculous. Okay, fine. We'll use the eraser. Okay. x0 is non-zero and x1 is non-zero. So what does the mirror look like? We have x21. This is x0, x1, x2 equals 1 plus y. And this thing has a map to C just given by either side of this formula, 1 plus y. And we can look at kind of what the special fibers of that are. So one special fiber is when x0, x1, x2 is 0. And so at this special fiber, the singularity kind of looks like we took a torus and collapsed it. There's a second, so this is at 0. There's a second special fiber at 1. And that's really just a missing fiber, right? Y is not allowed to be 0, so 1 plus y can't be 1. And in this picture, we have two kind of obvious, well, not necessarily obvious, but kind of symplectically standard families of tori. Here's one. These are the Clifford. And here's the other. These are the Chekhanov tori. Clifford should be capitalized. Okay, so we see on one side two kind of algebraic torus charts, and on the other side two kind of symplectic, two Lagrangian tori. There is some kind of story in the other direction, but it's a bit more involved. So I'm going to kind of continue this pattern with the kind of obvious C star to the n charts and the obvious tori. And the general statement is that we have m plus 1 of these. Kind of for every x, we can ask that only that x is allowed to vanish. So this gives us m plus 1 C star to the m plus n charts. But these don't cover everything because precisely, well, I said only that X is allowed to vanish, but the space contains kind of loci where multiple X's vanish. So this is not the whole thing. All right. So to solve this problem, either we need to figure out how to do Floer theory with kind of other Lagrangians that aren't mirror to these charts, or we need to find some replacement. Why do I say non-immerse Lagrangians? I guess I should probably back up a page. So there's kind of we could try to deform these Clifford the Clifford tori into Chekhanov tori, and one way we can do that is by kind of lifting it in some non-exact direction, and then we can honestly Hamiltonian isotope it if we do that. But if we want to keep it exact, then kind of we're going to have to pass it through this through the kind of most singular point in that singular fiber, and so we're going to end up producing some interpolating Lagrangian, which looks like that and passes through the singular thing. And the singularity associated to this is the cone over two tori. I should say in X11 there's a similar story, but there the singularity is the cone over two circles, and while the cone over a circle is smooth, it's just a disk, the cone over two circles is two disks which meet transversely at a point. So in X11, this singular Lagrangian, which interpolates between the Clifford and Chekhanov pictures, is immersed, but in X1 or in X21 it isn't. In X21, this thing has worse singularities, and we need to deal with that somehow. All right, let me talk about our strategy. So the strategy to get kind of this mirror symmetry with closed torus-like Lagrangians, well, is first we're going to produce a Lagrangian. Oops. An immersed Lagrangian, LMN inside XMN. And we're going to kind of also produce a preferred space of kind of objects supported on it. So I'm going to say together with a space def geo is going to be of what we're calling geometric deformation cochains. Okay. So that in that space of geometric deformation cochains, we're going to aim to find a kind of copy of the mirror. And so we're going to want to say that the objects that we get there are the mirror. So we want to identify the space of non-zero objects or deformations of def geo with point on the mirror. Now, well, if someone asks, I'll talk about, do I mean like actual deformations or formal deformations? Somehow what we'll end up doing is producing kind of a condition for an object to be non-zero, and we're going to kind of identify which object that is, and then you're basically just asking what ring are we working over, which I'm fairly sure the theory is actually agnostic to. In any case, we do need to figure out which point is which.
So when you mean the theory is agnostic,
Yeah.
but if you want to work over C, you'd have to maybe prove some convergence of some stuff. Can you do that?
No, if I want to work over C, I stick with these exact Lagrangians where I only have a finite amount of data.
Okay.
So this Lagrangian LMN is kind of some exact immersed Lagrangian.
Okay.
So we end up, if we want to work over C, we can just work in the ordinary kind of category of exact Lagrangians, and we can find all of these points as objects of that category. Now, obviously, non-exact perturbations aren't, what do I want to say? They're not like actual exact Lagrangians, but they're still objects of the category in the sense that kind of we can find them, we can build them out of this deformation space, and this deformation space is just like C, or kind of is generated over C by some intersection points.
Okay.
Kind of, if we worked over the nova covering, then these would, in a sense, be kind of the kind of deformations that we would kind of be studying. To get these non-exact deformations are like necessarily going to be kind of non-zero valuation, but kind of and somehow you don't need to kind of actually transfer things from lambda to C. If you want to work over C, you can just work over C. Now, when you want to do family-Floer theory, you should just work over lambda. And then there's some kind of question about kind of whether you can globally piece this together over C. And that's not a question that I am prepared to answer. But kind of for the purposes of understanding what the local, like of just producing the mirror, the local mirror that you can then attempt to piece together, it doesn't matter.
Okay.
So in any case, we need to be able to identify which point kind of a given object is mirror to. Now, these XMN are affine varieties, so points on them are, well, you know, particular modules. They're on which kind of the kind of coordinates take kind of act as some number. So kind of identifying which points these are kind of we can do once we have a mirror to the structure sheaf. Do this. We need a mirror to O. And I should say, again, when the goal is to piece things together, you're going to have some charts where your fibration is smooth, or at least smoother, right? Your SYZ fibration. And if we're interested in piecing this together, we need to figure out kind of a fiber in this smooth chart and a deformation of this immersed Lagrangian. How do those match up? And we can do that because once we're in the overlap, the fiber in the smooth chart gives us some actual Lagrangian in XMN, and we can ask, are these isomorphic in whatever Fukaya category we study? And so if we have a mirror to O just in XMN, that's enough to identify these things. Maybe I should see if there are any other questions before I continue to how we do some of this. Oh, is my video the wrong video? That's unfortunate. Oh, it's the wrong video because the right video is not plugged in. Okay, any case.
Cool. Oh, nice. No questions?
By the video.
What's that? Yeah, the video is better. I solved the problem.
The video is better, but the audio is not as clear.
Oh, oh no, really? It switched the audio? How's this?
You have to say something.
Is this better? No?
No, it stayed the same, I think.
Oh no, so I broke the audio? Okay, well,
so the starting point is a particular projection, which we've seen before. So kind of this standard projection is 1 plus the sum of the y's, which of course is just the same thing as the product of the x's. So either of those gives a formula for the standard projection. And we can ask, kind of, what did this projection look like? How does it compare to what happened with the kind of the simpler examples? So it's again the case that we have kind of a special fiber at 1 and a singular fiber at 0. But I'll start with the general fiber. So the general fiber kind of obviously splits under kind of, there's some equation for y and some equation for x, right? So the general fiber is c star to the m that's coming from the x's. We have the product of the x's is some non-zero quantity cross some pair of pants. Am I doing the superscript? Yeah. H n minus 1. So this is with the y's, those are with the x's. So just to be clear, the pair of pants h n minus 1 is 1 plus sum of y equals 0. Okay, so that's what happens over a general point. What happens over the singular point at 0? So the singular fiber at 0 looks like the product of the x's is 0. So that looks like kind of some normal crossing thing with a bunch of pieces, right? That's the union of the coordinate hyperplanes. Cross a pair of pants. I'm going to ignore that pair of pants for now. And there's a special fiber at 1. Now, in the example that we did, this was still a missing fiber, but in general, it looks like the sum of the y's is 0. And when there's more than one y, that is a non-trivial fiber. This is equivalent to h n minus 2 cross c star. Okay, so this is kind of the standard projection that I'm going to be working with the entire time. Now, what is our Lagrangian? Well, it lives over here. It fibers over this thing. And kind of concretely, the Lagrangian L Mn is R plus to the M, I guess what do I want to say? Sure, I'll just say M plus N. And what are the coordinates on this? You know, it's x1, xn, y1, or m, y1, yn. So in fact, if this is the case, then x0 is also a positive real number, because x0 is, you know, some positive thing divided by a bunch of other positive things. And it's, well, 1 plus a bunch of positive stuff has to be positive, so the entire thing lives over this ray. So that's the Lagrangian. Oh, sorry, sorry, this is not LMN, this is OMN. This is mirror to the structure sheaf, which I'm just calling O to make it easy to remember. Okay. So our theorem, kind of the starting point, which is just wrapped mirror symmetry, says that there's an equivalence of, I guess I'll say A infinity categories between the split closure of the wrapped Fukaya category of X Mn and perf of what do I want to say? X and M. I guess I could write co. These are all smooth things. I'll write co. And this sends O Mn to O. So so basically, there is some equivalence that realizes homological mirror symmetry between XMN and XNM. This is completely illegible. Okay. So there's two things I should say about this. So the first is that it's enough to show that OMN has, well, I'll say split generates first. And has the right endomorphism algebra. Because, well, co is generated by O. And so if I have a map on on generators, I can extend that to a map on perfect complexes. Okay, so in our case, we'll build an equivalence sending OM and to a line bundle which kind of, well, obviously after some auto equivalence of one of the categories is the same as sending it to O. Now, I don't want you to think of this this line bundle as some like interesting twist between the A and B models. This is just a difference in conventions for descent formulas. There are natural formulas that you would try to write down in the A model versus in the B model, and kind of the formulas you would use to piece things together differ by a twist. That doesn't mean that the theories differ by a twist. That just means that kind of the formulas that people happen to write down do.
I'm sorry. So can you just I missed the construction of the Lagrangian or m comma n. Can you just quickly repeat it?
Yeah. So xmn. Let me give the formula for this thing again. This is product of the x's is 1 plus sum of the y's. And I just take OMN to be all of the x's and all of the y's are in R plus, are real positive numbers. So by default, oops, this thing is in kind of CM plus 1 cross, this is too small. This is in CM plus 1 cross C star to the n. So it makes sense to ask about things being real positive. And if we do, we get kind of, it's some, actually it's not even really a calculation that this is Lagrangian, kind of, it's basically, you have something which is Lagrangian in the ambient space, you intersect it with xmn, and it's a Lagrangian in xmn. So this is Lagrangian, and the claim is it projects over this green ray. I guess the other claim is that it's like a complete Lagrangian, despite the fact that.
Okay, thank you. I understand.
Yeah, R plus doesn't kind of seems to just stop at 0. Okay. Yeah. So the difference is a matter.
So can I ask you a question about your theorem?
Yeah, absolutely.
So do you prove your theorem via family flow homology, like you mentioned earlier, or is some other?
No, everything I'm going to talk about today is kind of much simpler than family flow homology.
Okay.
So yeah, this theorem we're going to prove by a gluing construction. And kind of, I'll state another theorem that I won't get to, but that's the other theorem is an explicit computation of holomorphic curves. So let me say, how do we prove this first theorem? So the starting point is that we want to interpret this xmn as a gluing. And what do I mean by that? I'm going to just cut it apart in the base. So I have the piece which lives over the left-hand side and the piece which lives over the right-hand side. Really, these pieces are Liouville sectors, and we have a theory for how to glue Liouville sectors together. So what do we have in the middle? Let me move this over so everything lines up nicely. So in the middle, we have the wrapped category of the fiber. So that's of C star to the M cross H n minus 1. Great. So this thing is mirror to co on, well, again, C star to the M cross, what do I want to call this? I guess I'll write it explicitly. Product of the xi equal, or I guess xj in this case, equals 0. All right, so it's the C star is mirrored to C star, pair of pants is mirrored to coordinate hyperplanes. This equivalence was, well, the equivalence for the right-hand part was proven by Lakili and Polishchuk. And we get the full thing by Knuth. Okay, let's talk about the right-hand side. So on the right, we lose our singularity for the x's. So on the right, we basically just have this C star to the m in the fiber cross something interesting happening with the y's, right? So the x's are the C star, the x fiber is the C star to the m, the y fiber is the pair of pants, and something special happens in the y components. So on the right, we have, again, C star to the m cross. So what is happening with the y's? We have, what do I want to say? Well, the y's now include the special fiber. So in total, we see all of C star to the n. But now there's some superpotential or some stop. And that stop is, or the superpotential is sum of the y's. Oops. Sum of yj. So this is mirror to C star to the m cross, and C star to the n with this superpotential is just mirror to Cn. So here I can put W again, and here I can put Co again. I'm going to give myself a little bit more space. So this equivalence is due, I mean, there are various ways of doing it. Like lots of people have proven mirror symmetry for Cn. The version that works best for us is to use FLTZ mirror symmetry. Plus kind of technology developed by Ganatra-Pardon and Shende. Okay, so on this right-hand side, we have, there's kind of a push forward map on sheaves, I lower star, associated to the inclusion of the coordinate hyperplanes inside Cn. On the A side, we have a cup functor. And I'll remind you, the cup functor takes a Lagrangian in the fiber and it parallel transports it over an arc which goes along the stop. In this case, we just think of the right-hand side of this. I guess you can't see it, but I'm holding my hand over the left hand, over the left half of the picture. And so this dashed blue line is the stop for the right-hand side, and the red line is an arc that goes along the stop. Okay, so that's the right-hand side of this picture. What happens on the left? Well, on the left, we just have this pair of pants fiber floating around. So we have something cross H and -1. But what is happening with the x's? Well, now we have all of C m plus 1. They can be anything with this superpotential product of the x's, product of xi. So I have the wrapped category of that. What is this mirror to? Well, the pair of pants is mirror again to the union of the coordinate hyperplanes. And what is Cm plus 1 with this potential mirror to? It's mirror to a pair of pants. It's mirrored to a lower dimensional pair of pants, to be precise, Hn-1. And here I do want to put co again, not perf. And again, we have functors going this way. Now Hn-1 is a hypersurface of C star to the m, and we have a restriction functor on coherent sheaves, and the other component just floats around. At the top, we have another cup functor that gives us, to the other side of the stop. And this mirror symmetry statement, the kind of part we need to add is between the stopped copy, or this Cm+1 with the superpotential and the lower dimensional pair of pants. And that was done by Abouzaid and Aru. Okay, so in total, we have this big diagram of kind of A side categories at the top, B side categories at the bottom, and some data of how they're glued together. Any questions about any of this stuff?
Can I ask one question?
Yeah.
Zack. So wondering on the B side, why the bottom becomes a I upper star? So there's like this symmetry. On the top is very symmetrical. It's just a cap. On the bottom, how to understand
I mean,
this?
somehow it has to do with kind of the difference between like Calabi-Yau hypersurfaces and hypersurfaces of Calabi-Yaus. So on the right-hand picture, you should think of this, at this bottom, this coordinate hyperplanes, including into C, as like some anti-canonical divisor of C, or of Cn. And so cup is mirrored to inclusion of the Calabi-Yau creature, right?
Okay.
Kind of this thing in the middle is Calabi-Yau.
Okay.
Kind of is extremely Calabi-Yau. But when you have a hypersurface in some Calabi-Yau, kind of the way that things match up is different. So basically, you should always think of the domain of cup as being some symplectic Calabi-Yau thing, right? Like the fiber is some unstopped Liouville domain, which we generally pretend is Calabi-Yau. But kind of the thing which is Calabi-Yau at the bottom is again, this is the pair of pants, is again C star to the M, and not the pair of pants. Well, technically, I guess the pair of pants is trivial, whatever, but kind of from the perspective of the theory, we think of the pair of pants as being some hypersurface in the Calabi-Yau manifold C star to the M.
Okay.
Does that help?
Okay, thanks. Yeah, thank you.
Okay. All right, so let's talk about how we do this. And I've put a copy of the diagram in the lower left. So the first step is to form the directed gluing. Which is going to be a copy of XMN, but it's going to have some stop Y. And what stop is that going to be? I'll put this over here. There's going to be a stop there. So what we're doing is we're gluing. We're going to glue, but we're going to retain one stop. So when you glue, usually you kind of glue along the stops and then there's no stops left, but you can you have two sides of the original stop. You can retain a stop on one side or the other, or on both. So here I'm retaining a stop on one side. Okay, so what does gluing say? Gluing for W says that the wrapped Fukaya category of this stopped domain, XMN with the stop, is given by some semi-orthogonal decomposition where the kind of first term, let me say that the Rave vector field kind of goes counterclockwise, but here it kind of gets stopped, right? So it doesn't go across. So the thing on the right should come first. If I could have put the stop at the top, and then it would have gone the other way. That's part of this like difference, part of the question of what convention do we take. So the thing on the right is this upper right thing in the diagram. That's W of C star to the M cross C star to the N with sum of Yj as my stop. That's the first component. The second component is the thing on the left. So I have W of C, not C star, C M plus 1 cross H n minus 1, stopped by product of the xi. So we get that semi-orthogonal decomposition. So if I just apply mirror symmetry, this looks like co of C star to the M cross Cn on the left, and co of H M minus. Did I really switch from top to bottom? Oh no, I did. Whatever, I'll put it at the top here. Do I have a reason? Whatever, I'll put it at the top. M minus 1 cross this locus, this mirror pair of pants. I'm just going to write it as the mirror pair of pants, actually. Oh, that's why I moved it to the bottom. I see, fine. Product of xj equals 0. So this is, by Orloff's theorem, co of some blowup is the blowup along this these coordinate hyperplanes of C star to the M cross Cn. Okay, so what we've done in this first step is we have identified XMN with a stop as mirror to some blowup of C star to the M cross Cn. So the next step is just to remove the stop. So Rabchukaya category of XMN is given, well, by stop removal. It's a quotient, the Rabchukaya category of the stopped thing, and stopped by y, modulo the image of this cup functor, and the cup functor here kind of looks like that. So I'm going to say cup applied to the Rabchukaya category of the fiber, which is this thing in the middle. C star to the M cross H n minus 1. So what does that look like? That looks like co on the blow up along h minus 1 cross product of the xj equals 0 of c star to the m. Oh wait, no, that's not. I'm confusing myself. Yeah. Cross Cn yeah. Right. Is that what I had? Yeah, cross Cn. Sorry. Modulo the image of this cup functor, which is the image of, well, some functor coming from this thing in the middle bottom in the diagram. I'm just going to call it I lower star because kind of you can compute that it's mirrored to inclusion of some divisor. And I'll say in a second what that divisor is, but it's the thing that we're looking at should be a copy of C star to the m cross coordinate hyperplanes. Okay, so where do we see a copy of C star to the m cross coordinate hyperplanes? Well, if we've blown up, then we should be looking at kind of the proper transform of kind of C star to the m cross coordinate hyperplanes, right? So the thing we're blowing up along is some codimension 1 piece of the right-hand divisor. And so kind of that kind of lifts to the blowup. Okay, so this thing is then kind of the blowup cross product of the xj equals 0 of C star to the m cross Cn minus, let me put this in bigger parentheses, minus the strict transform of this thing, C star to the m cross coordinate hyperplanes. So it's co on the blowup minus some locus. And so now I have a claim, which is that this thing is precisely XNM. And once we verify that claim, this is now some kind of fact about kind of affine varieties. This thing is the same as that thing. Then we've verified homological mirror symmetry. So let's do that. Actually, before I make that verification, is everyone happy with this? Everyone who wanted to follow happy with this descent computation? Okay. So I'm left with just kind of looking at what this blowup is. So if I take the blowup along C star to the, not along C star to the m, along some pair of pants, cross product of the x, cross the coordinate hyperplanes of the ambient space, C star to the m cross Cn. Well, kind of by definition, each of these things, right? The pair of pants is cut out by an equation. The coordinate hyperplanes are cut out by an equation. And so we have an explicit formula for the blowup. Well, it's something that lives in C star to the M cross Cn cross P1, right? So this thing has like the xj check. I guess these should be checks. I'll just leave out the checks. This has the yi. I'll put checks. We're working all in the mirror here. And this I'm going to give coordinates uv. And so it's given by u times the first equation, 1 plus sum of yj, that's the, or yi, sorry, yi check, that's the first, that's the pair of pants, equals v times the product of xj check. Okay. Now the strict transform of C star to the M cross, cross coordinate hyperplanes is, well, I'm just saying that I need the thing where the right-hand side vanishes, which means just u equals 0. So it's just the 0 locus of u. And so the complement is, well, 1 plus sum of yj check equals v over u times the product of xj check, or yi check, sorry. Which now lives in C star to the M cross Cn cross C. So this is yi check, this is xj check, and this is x0 check. And so this is just precisely x and m. Okay, so that verifies that this creature, that we got the rapid Fukaya category of xmn as being mirror to Sylvan is indeed x and m. All right, that's how we prove the theorem. Any questions, or should I go to kind of discussion of the other, or brief discussion of kind of the other part where we have to construct deformations of some Lagrangian?
It seems you can move on to the
Okay.
backgrounds.
All right, so let me move to the other part. So recall we have some projection, x, mn, mapping to C by some projection, rho n, which was 1 plus the sum of the y's. Now, let me draw a picture of that C. We have some special fiber here, or some singular fiber. We have some special fiber. And what we really want, let me put the special fiber over here. What we really want is this singular Lagrangian, but we can't have it. So instead, we're going to replace it with some cable. And the cable looks like this. So this is an immersed Lagrangian. It has double points here, here, and here. So L M N kind of should live over the green curve. So kind of we know what it is in the base, but we need to figure out what it does in the fiber. Okay, so I want to just say there's kind of an obvious solution, which is that the fiber is some, C star to the M cross some pair of pants. So take kind of R plus, or not R plus, take the 0 section, take kind of S1 cross L and cross L n minus 1, where L n minus 1 in the pair of pants is Sheridan's Lagrangian. Now, this probably works. Oh, sorry, not S1, some torus, right? TM. So this probably works. But it's not so easy to get a handle on. So what we did is we're going to cook up additional projections to C and reduce everything to curves in C. Okay. Let me maybe just say what these projections are and say what we get out of them. So row n, going back, we're thinking of as the last in a family. Oh, and I should maybe give this a name, L1. This green curve is L1. So row 1 is just 1 plus y1 over y2. Row 2 is 1 plus y1 plus y2 over y3, and so on, all the way to row n as 1 plus y1 plus yn over, and then we just imagine that yn plus 1 as being 1. And the divisors di, or I should say dj, which is rho j inverse of 1. Well, if rho j is 1, that means that the sum of the first jy's is 0. Oops. And that's the same thing as rho j minus 1 being 0. So what this lets us do, what do I want to say? Well, why don't I just continue? Together with the x's, these projections define a complete set of coordinates, and so we can take Lmn to be Tm cross L1 to the n. So we can use each of these rows to get a copy of L1, and when we put this together, we get a sensible Lagrangian. The theorem is that the objects are kind of, well, the objects supported, given by Lmn twisted by some sum of kind of well, no, I'm out of time, and oh, okay, sorry.
You don't need to worry about the time. You can.
Okay.
Be very flexible.
Okay. Let me say what this Lagrangian is. Let me say what the deformation space is, and then let me state the theorem, and then I'll stop. So def geo should be some piece of CF1, some piece of kind of the degree 1 Floer cochains on which we impose the Maurer-Cartan equation. So I'm just going to take H1 of Tm, H1 of the torus, plus the degree 1 self-intersections and if I go back, it turns out that there are 2 degree 1 self-intersections and 1 degree 2 self-intersection on L1. So each copy of L1 gives me 2 generators. So in total, this has 2n generators. All right. And so the theorem is that the variety, well, of geometric deformations where EF star of LM and beta is not 0. So the non-zero objects of this deformation space is isomorphic to X and M. There's kind of some further part about it being isomorphic in a way compatible with, we can identify which point is which, use by acting on it with by endomorphisms of OMN. But I'll stop at this point.
So you're saying that this def geo, they all satisfy the Maurer-Cartan equation? Is that what
yes,
you said?
these all satisfy the Maurer-Cartan equation.
Okay, and the ones that have non-trivial one is. Okay. And can you explain again exactly what is the Lagrangian? What is?
Yeah, so let me actually just make a new page and just start drawing some pictures.
Okay, thank you.
So kind of in each, I'm going to ignore the X components. Somehow the X components are pretty straightforward. We just see this like torus. So for now, I'm going to ignore that. So here's my L1. And I have this in each of these row components. And they all kind of look similar. Well, no, I should say, I'll say it in a second. For row J, where J is not n, this star fiber is smooth. But if I put this as like row, whoops, if I call this like row J and row, let's say J minus 1, then the thing over 1 is dj, and then this is also dj. But here dj is a smooth fiber, so I should just mark it with a point. So here's dj minus 1, here's dj plus 1. So kind of when we count holomorphic disks, it turns out that kind of there's kind of this vertical reflection symmetry, and all of the holomorphic disks come in pairs that are determined by one of the vertical reflections. So there's like a main component that I give it, right? These rows give me different kind of components of this thing. And there's one main component where all of the, so given any holomorphic disk, kind of there's some main component that it lives in, and then there's a corresponding holomorphic disk associated to that vertical reflection. So every holomorphic disk that would contribute to the Maurer-Cartan equation cancels with some other disk. So there are lots and lots of Maslov 2 disks, but they all cancel.
And what is that part of the Lagrangian? Just topologically? Kind of having a hard time.
It's an immersed torus. Right? We have kind of a torus cross a bunch of these things, and each of these are immersed circles.
Okay. And you said only some of the self-intersections. How many are there?
So there are 3n self-intersections, but only 2n of the, well, sorry, there are 3n degree 1 generators, right? So there are many, I mean, there's entire spaces of self-intersections, right? Like every time you see a self-intersection, you cross it with anything on the other, in the other components, and you get a self-intersection. So these self-intersections aren't isolated, but there are kind of isolated generators. Or sorry, we're not interested in isolated generators. We're interested in like, wait, do I call this isolated? Should I call it isolated? Yeah, I guess I should call it, I should treat it as isolated. Like if you perturb it by, if you put like some, right, these come in like more, like intersecting more spot families. And if you perturb that, then you get isolated things. So each component gives you, each copy of L1 gives you 2 of these generators.
Okay, so was that all you wanted to say? Or you?
I think that's all I should say.
Okay. So thanks a lot. It was a very interesting talk. So maybe now other people other than me might want to ask questions. So please go ahead. Okay. Last chance. No one has questions. Okay, so I think you did too good of a job.
I think I did the opposite, but